Welcome to AI Frontiers, where we explore the cutting-edge research that's reshaping artificial intelligence. Today we're diving into 17 groundbreaking papers from October 29, 2025, all from the computer science machine learning domain. We'll discover how AI systems are developing alien forms of intelligence that think completely differently than humans, yet achieve superhuman performance. From chess strategy to medical diagnosis, these findings reveal why the path to artificial general intelligence might be more alien than we ever imagined. Picture this. A chess grandmaster sits across from an AI system, both staring at the same board position. The human sees a knight outpost, recognizes the importance of controlling the center, and feels the tension between piece safety and aggressive play. The AI sees something else entirely. Despite playing at superhuman levels, the artificial mind has developed an alien form of intelligence that bears little resemblance to human strategic thinking. This isn't science fiction. It's the startling reality uncovered by researchers studying how AI systems truly understand the world around them. Both achieve superhuman performance, yet their internal reasoning processes couldn't be more different. These 17 papers from October 29, 2025, reveal a field in fascinating transition, where researchers are grappling with fundamental questions about intelligence, learning, and the future of human-AI collaboration. The computer science machine learning domain sits at the epicenter of these discoveries, as scientists work to understand not just how to build better AI systems, but how these systems actually think and learn. The research shows us a field wrestling with profound questions about the nature of intelligence itself, while simultaneously pushing the boundaries of what artificial systems can achieve. Computer science machine learning sits at the heart of the AI revolution, like the engine room of a massive ship powering everything from your smartphone's camera to autonomous vehicles navigating busy streets. This field encompasses the algorithms and mathematical frameworks that enable machines to learn from data, recognize patterns, and make decisions without being explicitly programmed for every possible scenario. Think of it as teaching computers to fish rather than giving them fish. We're developing methods that allow machines to discover knowledge and improve their performance through experience. What makes this field particularly captivating is its interdisciplinary nature, where computer science meets statistics, mathematics embraces cognitive psychology, and theoretical insights collide with practical engineering challenges. From recommendation systems that curate your social media feed to diagnostic tools revolutionizing healthcare, machine learning has become the invisible backbone of modern digital life. This research represents humanity's attempt to replicate and understand intelligence, one of the most fundamental aspects of consciousness. The first dominant research theme centers on human-AI alignment and interpretability, the crucial question of whether AI systems truly understand concepts the way humans do, or whether they're sophisticated pattern matchers creating an illusion of understanding. This theme emerges most dramatically in research by Lomasso and colleagues, who use chess as a lens to examine how neural networks encode human strategic concepts. Their findings reveal a profound paradox. Early layers of transformer networks encode human strategic concepts with remarkable accuracy, up to 85% alignment with how grandmasters think about the game. However, the deeper layers responsible for the AI's superior performance show only 50–65% alignment with human concepts. Imagine teaching someone to paint by showing them thousands of masterpieces, only to discover they've learned to create beautiful art through completely different visual principles than any human artist has ever used. This research suggests that performance and understanding may be more separable than we previously assumed. The second theme focuses on efficiency and optimization in learning algorithms, addressing the computational challenges of deploying machine learning systems in resource-constrained environments. Think of this like automotive engineering. We're not just building more powerful engines but designing systems that achieve better performance while using less fuel. Researchers are drawing inspiration from biological neural networks, exploring how the brain's energy-efficient learning mechanisms can inform artificial systems. New predictive coding networks achieve a remarkable 50% reduction in computational steps while maintaining learning performance. These biologically inspired algorithms mimic how the brain processes information, opening possibilities for neuromorphic hardware that could revolutionize edge computing applications. The efficiency revolution represents a crucial step toward making powerful AI accessible in smartphones, medical implants, and autonomous systems where computational resources are limited. The third prominent theme tackles the messy reality of real-world data. Unlike the clean, well-structured datasets used in academic research, real-world information is often incomplete, noisy, and unpredictable. This includes work on survival analysis that must account for patient diversity and temporal changes, research on learning from uncurated data pools, and studies on graph neural networks that must remain robust under various attacks. It's like the difference between learning to drive in a controlled environment versus navigating rush-hour traffic in a thunderstorm. The development of robust watermarking techniques for graph neural networks represents a crucial advance in protecting intellectual property for AI systems. Think of this like creating unforgeable signatures for AI models, a way to prove ownership that remains intact even when models are modified or fine-tuned. This breakthrough addresses critical needs in the commercialization of AI technology. These 17 papers reveal several groundbreaking discoveries that could fundamentally change how we think about artificial intelligence. The most philosophically significant finding shows that as neural networks optimize for better performance, they develop increasingly alien forms of intelligence that diverge from human thinking patterns. Another breakthrough involves predictive coding networks that achieve a remarkable 50% reduction in computational steps, while maintaining learning performance, opening possibilities for neuromorphic hardware revolution. In medical applications, researchers developed sophisticated frameworks for modeling patient diversity and survival analysis, with a dual mixture of experts approach that automatically identifies different patient subgroups. While a 0.04 improvement in concordance index might sound modest, in medical contexts such gains can mean the difference between life and death for many patients. Perhaps most remarkably, researchers demonstrated how high-quality training data can be automatically generated from existing scientific literature, with synthetic data leading to substantial improvements across medical AI benchmarks. Our paper of the day represents one of the most profound investigations into artificial intelligence we've seen this year. The research by Lomoso and colleagues chose chess as their testing ground because it offers something unique, a domain where human creativity and strategic thinking meet precise, well-defined concepts that can be objectively evaluated. Chess masters think about center control, piece coordination, pawn structures, and tactical motifs. These aren't just abstract concepts, they're concrete strategic principles that have been refined over centuries of human play. The researchers analyzed a 270 million parameter transformer model that plays chess at grandmaster level, examining how different layers encode human strategic concepts. Their methodology involved training linear probes on each layer to predict human expert annotations, essentially asking, how well does each part of this AI system understand chess the way humans do? They also created the first Chess 960 dataset to eliminate memorization effects, providing a clean test of true strategic understanding. The results reveal a striking and troubling paradox that has profound implications for AI development. The early layers of the transformer encode human concepts with remarkable fidelity, achieving up to 85% alignment with how human masters think about strategic positions. These layers seem to develop representations that closely mirror human chess understanding, identifying important patterns like knight outposts, weak squares, and piece activity in ways that human experts would recognize and approve. But as information flows through deeper layers, the very layers responsible for the model's superior chess performance, something remarkable and concerning occurs. The alignment with human concepts drops significantly, falling to just 50–65% accuracy. The AI develops strategies and pattern recognition that are undeniably effective for winning games, but fundamentally alien to how humans conceptualize chess strategy. When tested on Chess 960 positions that eliminate opening memorization, concept recognition dropped 10–20% across all methods, suggesting that apparent understanding was partially dependent on memorized patterns, rather than true strategic comprehension. The implications of this chess research extend far beyond the game itself, forcing us to confront uncomfortable questions about the nature of intelligence and AI safety. This research suggests that as AI systems optimize for performance, they may naturally evolve toward forms of intelligence that are increasingly difficult for humans to understand or predict. It's like discovering that your most successful student has been solving math problems using methods that work perfectly, but that you can't follow or verify. If we can't understand how AI systems make decisions in a well-defined domain like chess, how can we trust them in life-or-death situations like medical diagnosis or autonomous driving? For the field of explainable AI, these findings present both challenges and opportunities. The challenge is that the representations driving superior performance may be inherently difficult for humans to understand. The opportunity lies in discovering that early layers do maintain human-aligned representations, suggesting we might design architectures that preserve interpretability without sacrificing too much performance. This research forces us to reconsider the relationship between performance and understanding in artificial intelligence systems. Looking toward the future, this research landscape resembles a vast ocean of possibility, with researchers serving as explorers charting unknown territories of intelligence and learning. The most immediate frontier involves developing AI systems that can maintain human interpretable reasoning while achieving high performance. The chess research suggests this isn't impossible. Early layers do preserve human-aligned concepts, but it will require careful architectural design and training procedures. Another promising direction involves the continued development of synthetic data generation techniques that could democratize AI development by reducing dependence on large, expensive datasets while addressing privacy concerns. The integration of biological principles into artificial learning systems represents another frontier with enormous potential, with efficiency gains suggesting we're only beginning to tap into computational strategies evolved by biological systems. Future neuromorphic hardware could bring these efficiency benefits to edge devices, enabling powerful AI capabilities in smartphones, medical implants, and autonomous systems. Perhaps most importantly, the field is moving toward more nuanced approaches to AI safety and alignment, developing domain-specific methods for ensuring reliability, fairness, and interpretability. Today's journey through the frontiers of machine learning research reveals a field in dynamic transition, grappling with fundamental questions about intelligence while pushing the boundaries of what's possible with artificial systems. We've seen how AI systems can develop alien forms of intelligence that surpass human performance, discovered new ways to make learning more efficient and robust, and explored methods for ensuring AI systems remain trustworthy and aligned with human values. The chess research reminds us that the path to artificial general intelligence may be stranger than we imagined, with AI systems potentially developing forms of reasoning that are effective but fundamentally different from human thought. The efficiency breakthroughs show us that biological inspiration can lead to more sustainable AI systems, while work on fairness and robustness demonstrates the field's growing maturity and responsibility. These discoveries matter because they're shaping the AI systems that will increasingly influence our lives, and understanding these developments helps us make informed decisions about how to develop, deploy, and govern artificial intelligence as it becomes more powerful and pervasive. This analysis was created through AI synthesis using Claude Sonnet 4202505514, with text-to-speech synthesis powered by Deepgram and image generation through OpenAI systems. The content underwent human expert review and validation to ensure accuracy and clarity. While every effort has been made to accurately represent the research findings, potential oversights may exist in this synthesis. The original research papers contain nuances and details that our overview could only begin to capture. We encourage listeners to engage with the primary sources and share their thoughts about these developments with colleagues and friends. The future of artificial intelligence isn't just being shaped by researchers in labs, it's being influenced by the broader conversations we have about what we want from these systems and how we can ensure they benefit humanity. Subscribe to the AI Frontiers channel for weekly deep dives into cutting-edge research, where we make complex concepts accessible and foster community discussions about AI's future. Your engagement with these ideas helps determine which frontiers we'll explore next. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archivepreprinserver.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archivepreprinserver.org.